10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Ladies and gentlemen, as we are about to begin, please make yourself comfortable. I hope everybody will stay tuned throughout the second day of our conference. I have a few housekeeping announcements before we begin today's program. First, kindly mute your device to avoid interruption. And secondly, if you have any question, please drop to the floor via chat here on my left. Thank you for your kind cooperation and attention. Assalamualaikum and good morning. Ohayo gozaimasu, Jashanghao to all speakers and participants. My name is Dr. Nurul Najah from University Technology Mara Malaysia, UiTM, and it is my pleasure to be your MC for today's session. On behalf of committee, I would like to extend a very warm welcome to all of you to second day of 17th ASEAN Symposium on Medicinal Plant and Spices. I hope you will find the program we have lined up for you to be fruitful and engaging. Without further ado, I would like to invite Professor Dr. Nur Hadiani Ismail to introduce our first plenary speaker for this morning and chair the session. Professor, the floor is yours.
Assalamualaikum and good morning, everyone. Today is the second day of our much awaited ASOMPS, and I'm very happy to be here today on the second day to introduce our dear friend, Professor Geoffrey Cordell. Professor Cordell is not a stranger to the ASOMPS community. Okay, he has been with ASOMPS for a long while, and in fact, for this 17th ASOMPS, he has played a very special role in advising us in the drawing up of the scientific programs. So, but I will do the task assigned to me to formally introduce Prof. Cordell. So I will read his biodata, which is very, very illustrious. Professor Emeritus Geoffrey A. Cordell obtained his PhD in indole-alkaloid chemistry at the University of Manchester in 1970. And after 2 years at MIT, he joined the College of Pharmacy, University of Illinois at Chicago. Holding several senior administrative positions at the college and campus level, he retired in 2007. He is the author of more than 600 research publications, reviews, book chapters, and professional contributions, 2 books on alkaloids, and is the editor of 37 books, including 29 volumes in the Alkaloids Chemistry and Biology series. I don't know whether I can ever write that much. Prof. Cordell is on the editorial advisory board of 30 international scientific journals and has been a plenary speaker at over 185 international meetings, including many in the Asian regions. An honorary professor at universities in China, India, and the Philippines, and he is also a visiting professor in UiTM Malaysia, Japan, Thailand, Mexico, Brazil, Peru, and Colombia. He was named Outstanding International Ethnopharmacologist of the Year in 2015 by the International Society of Ethnopharmacology and received the Norman Farnsworth Research Achievement Award of the American Society of Pharmacognosy in 2019. Where he is an honorable member and a former president. He presently assists governments and corporations in the development of traditional medicines and universities in assessing their administrative, academic, and research programs, including many in Malaysia. He also provides lectures and workshops on natural product drug discovery, traditional medicine quality control, and grant and manuscript writing and reviewing. His interests include the chemistry biological activity and synthesis of alkaloids, ecopharmacognosy, medicine security, and this is a very, very big word that I'm going to have problems pronouncing. Cyber eco ethnopharmacolomics. Okay, there's a new term that he's going to be speaking today, and the role of natural products in the fourth industrial revolution. Please, Jeff, the platform is yours. Thank you.
Thank you very much. Let me get my slides up here. There we go. All right. Am I being heard okay? And can you see the slides okay? All right, let's begin. So I'm going to speak today mostly about the future and about the interrelationships of a variety of technologies with respect to a term that I coined a couple of years ago, cyber-eco-ethnopharmacolomics. And I have a collaborator in this presentation, Dr. Shana K. Daly, and she's giving a lecture later on this morning with relation to synthesis and of natural products. Down here at the bottom of the first slide, you'll see some references. The cyber-eco-ethnopharmacolomics was first discussed in this Journal of Ethnopharmacology paper. And then there's a couple of relevant articles, one in Molecules, we'll talk about a little bit later, on alkaloid drug discovery, and one on various aspects of 4IR, the fourth industrial revolution, the quintuple helix, and the impact on natural products. And that's published in Natural Product Communications. So those are available. I'm going to start by dedicating this lecture to a very dear friend of mine, Ajahn Nishsari Ruangwongsi from Chulalongkorn University, Thailand. He unfortunately passed away on July the 30th this year, just a few weeks ago. And ironically, we had met at ASOMPS meeting in Bangkok in 1980. So we have been friends for 41 years. And we collaborated on a lot of research, and we published no less than 32 papers together, as well as training some PhD students together. So I miss him. He was a very dear friend, a very special friend. And so this is for him. On a happier note, coming up very soon, August 31st, is the 80th birthday of a very dear friend as well, Professor Yoshinori Asakawa, who is giving a lecture later on this morning. So Yoshi, I'm sure everybody who's on the line now is wishing you a very happy 80th birthday. Thank you for years and years of wonderful friendship, a lot of fun together in Chicago, in Morocco, and in many other places around the world. So natural product studies today are in many ways fairly traditional. There's the organism identification step, there's isolation, structural elucidation, biological activity, and biosynthesis studies, and all that means, and all the information that generates. If you want to make it more focused, there are drug discovery initiatives based on plants, microbes, and marine organisms. And then there's, of course, the issue that is affecting a lot of us these days, the quality control of prescription products, over-the-counter drugs, traditional medicines, dietary supplements, and cosmetics. And my friend Dian Guo is going to be talking about some of the quality control issues and some of his wonderful work on traditional medicines right after this. What about the future? Where are we going in the future? One of the challenges that we've seen for the last few years is the integration of new technologies and data systems, whether that's been in the areas of metabolomics, metabolite networking, more recently mass spectral imaging, looking at molecular binding studies, and the ability to be able to model natural products in terms of their binding site on particular enzymes, and looking at active places where within the enzyme there are interactions taking place, and you heard some of that yesterday from Professor Norman Lewis. The other aspect that, of course, is changing the way we do business are the green transformations and the reagents that are associated with those, whether those are enzymes, vegetables, et cetera, et cetera. And we'll talk a little bit more about that in a little while. What's missing from this list, however? Well, there's a couple of major things missing. One of them, of course, is sustainability. And that's been a very hot topic for me for many, many years now. And another one, of course, is climate change. And everywhere around the world, pretty much, we are seeing the impact of climate change, whether that's in terms of fires, whether it's in terms of flooding, whether in terms of sea level rises. It's quite dramatic and a little frightening. And those of you who may be interested, the IPCC report 16 was just issued last week with respect to climate change, and it paints a very emergency, urgent picture of what is needed to be done at the government level across the world. We need to always remember that without the natural resources that we are dependent upon for our research, that society is dependent upon for many, many different aspects of life, fundamentals of life, there is no system for societal benefit. So as we go through this lecture, remember that these two aspects, and I'm not going to focus on particularly today, but these two aspects underlie and overarch everything that we're talking about and that we do. So let me talk about natural products and the future and what that might be looking like. A couple of years ago, now 4 years ago actually, I wrote an article on 60 challenges for 2030. And if anybody is looking for topics to investigate with respect to natural products, there's plenty of ideas in there. Those are very serious challenges of what can be done, what's needed to be done to change natural products research for the benefit of society. As I mentioned before, cyber-eco-ethnopharmacolomics was a term that I put together in 2019 and talked about in an article in the Journal of Ethnopharmacology. I talked about this a little bit early last year, just after the COVID situation started, and it was actually in Malaysia. And one of the questions that I got from Professor Hariani at the end of the lecture was, do you know anything about Fourth Industrial Revolution and the relationship to natural products? And I said no, and because I didn't. And it got me reading, it got me thinking, it got me, if you will, being creative about what was going on and how to discuss this. So the future today is really instigated because of her suggestion. And so we're going to talk today about the Fourth Industrial Revolution and the quintuple helix. And this is an article that was published in Natural Product Communications earlier this year. So what is the Fourth Industrial Revolution? If we go through the first three, and I'm not going to go through all these dates, I'm just going to give you some idea of what the main features are from these industrial revolutions. The first was bringing mechanization, bringing water power, bringing steam power to the systems that were in place at that time. Later on, we went into advanced production. Of course, cars, the online assembly of cars was major, bringing transportation systems, whether those were trains or cars or buses or whatever, to global transportation, and then the globalization of electrical grids. In the third part of the Industrial Revolution, we got into more chemical aspects. So you see all the plastics, all the polymers, everything that came out of that particular phase of chemistry development. The advent of computer systems, a computer that used to take up a whole room that now sits on your desk or actually is in your hand as a smartphone, as well as beginning of automated systems. The fourth industrial revolution represents the internet, and it's now beginning to represent cyber physical systems. And we'll talk a little bit more about some of those aspects and additional aspects of 4IR very soon. The key to this is that fundamental change results from disruptive innovation. So what do we mean by disruptive innovation? So in the last 20 or so years, we've seen amazing disruptive innovation. So if we think about in terms of phone, mail, TV, newspapers, we've now got a smartphone. Everything we need to know is pretty much on this smartphone device. TV shows, going to the movies, we've got Netflix, Hulu, TikTok. Again, it's all on your smartphone. Taxis, Uber, Lyft, changing dramatically the way that systems operate. Department stores, shopping malls, Amazon, all right? Global phenomenon and the corresponding systems in some other countries around the world, particularly, of course, in China. Hotels, motels, Airbnb has completely turned on its head what hotels and motels are all about. Private systems now. What does that mean for natural products? Well, of course, over the years, since the middle of the 19th century, we've seen all kinds of disruptive technologies in natural products. The first of all was the ability to degrade natural products and then to begin to synthesize them. Then along came chromatography in all its forms and as it's evolved today with very sophisticated UHPLC, orbital mass spec systems, et cetera, et cetera. Spectroscopy, UV, IR, mass spec, NMR, and going to ever more sophisticated systems, more delicate systems, more refined systems, more sensitive systems. In vitro and enzyme bioassessments. So rather than using live animals, we've gone to systems that are not animal dependent and rely on cells or enzymes, receptors, et cetera, et cetera. Genomics in biosynthesis, the ability to be able to look into a bacterium at its genome and say, well, here are some of the biosynthetic pathways that this organism can produce. And that might well be many more systems than are evident from the simple culturing, the simple approach to developing that organism in culture systems. That with care, some of those systems can be extracted from the genome and put into other systems, E. coli or Streptomyces lividans, and developed, and their biosynthesis studied and new compounds gained. Molecular modeling, and all of that means in terms of the structures of the compounds, their conformations, and their binding characteristics. And then, of course, enzyme structures, which are now dependent on very sophisticated and wonderful X-ray systems that can give you very refined structures of an enzyme, and coupled with molecular bonding, look at where those natural products are binding. Of course, all of this comes back to a data accumulation, that a lot of these systems, the genomics, the modeling, the enzyme structures, spectroscopy, all are relying on data accumulation in one form or another. And we're going to get back to that in just a little while. So one of the challenges that we have, one of the questions that we have here is, what's going to be the next disruptive technology for natural products? So the fourth industrial revolution has about 12 components to it. And there are about 7 of these that relate to natural products. Sometimes you'll see that the 4IR is indicated as Industry 4.0. So the 7 characteristics that relate to natural products are the Internet of Things, of how we relate on the Internet to various forms of information and transfer and relationships and communications, just like we're doing today. Additive manufacturing, 3D printing, it's also known as neurotechnologies, biotechnologies, and of course the whole wealth of technologies that are involved there. Systems integration, automated robots. So we're going to be seeing robots in the laboratory doing some things that phytochemists and chemists and biologists used to be doing, as well as this whole huge area of big data. Now, obviously, in this brief lecture, we can't go into all of these areas. So I'm going to pick out a couple of these, and we're going to take a little bit closer look. What's going to make the difference here is human creativity, that everybody has access online to an enormous amount of data. The difference and the progress within systems, whether that's within country, within universities, within research programs, is going to be human creativity and how the existing systems are interpreted and used specifically locally, or to develop systems internationally. What is the quintuple helix now? So the quintuple helix is based on the triple helix, and the triple helix focuses on the linkages that need to be generated for a productive relationship and societal development between academia, industry, and government. Let me be very clear on that, because I've been involved in some of these programs for many years in terms of drug discovery, that this linkage of academia, industry, everybody sitting around a table, everybody working together, no egos. Let me say that again, no egos, that everybody is working as a team to bring things together for a societal benefit. The fourth helix, the quadruple helix, is concerned with the knowledge society, of the ability to create, access, analyze, and utilize information and systems that are global as well as local. The quintuple helix brings a social ecology component. We might call that the sustainability component. It's about conservation. It's about environmental impact. It's about recycling. It's about energy conservation. It's about how we minimize the footprint. And of course, if you go back to the IPCC discussion that was published last week, this becomes a very important aspect of moving forward and of reducing the impact that we are having on the environment and on Earth in general. It's knowledge creation. It's the integration of all of these components that provides the input for innovation. And the innovation is targeted towards the Sustainable Development Goals. So I'm not going to go through these because we've discussed them before, but if you need a refresher, go back and look at the United Nations Sustainable Development Goals and see how some of those apply to natural products. So with all of this, with 4IR and with quintuple helix, what are the implications for natural products? Let's look at a country and what a country needs to be doing. So one of the challenges that a country has is how to balance importing allopathic drugs, because there are very few countries in the world that actually produce drugs, that actually have a fully developed, fully integrated pharmaceutical industry. So one of the challenges is in which ones to import, which ones to develop as part of a burgeoning pharmaceutical industry. How does generic substitution fit in with the brand name drugs? And how do you provide safe, effective traditional medicines in a sustainable, quality-driven, and affordable manner? How does that work? What are the systems for that? And we've talked a little bit about this in other lectures and one thing and another, so I'm not going to dwell on it today. But this becomes core for the health system of the country. One of the challenges, of course, we have is this gap, this healthcare gap that has to be bridged. What does that represent? It represents, on one side, traditional medicines which cannot be developed into full-scale drugs. It's too expensive, and not enough countries have the facilities to be able to do that. That's not a reasonable expectation within probably the next 30, 40 years for most countries around the world. So there's a compromise that's going to have to be made there. And that's kind of a whole other lecture. At the same time, synthetic drugs cannot meet global healthcare demands. There's a volume issue because we can barely deliver even an aspirin to everybody in the world. And there's a distribution issue. And of course, there's a cost/profit issue that some of these drugs are extremely expensive, both in the developed world and even more so, of course, in the emerging world. So how do we fill this gap? What's the role of natural products in beginning to fill this gap? And of course, one of the things that we've talked about in the past is the notion of a class of drugs that are natural product recommended medicinal agents. And it's a separate discussion as to what that constitutes and the quality controls issues there. Let's pursue a little bit for a moment some of the drug discovery issues with natural products, because a lot of people are working in that area. So we've got all kinds of natural product diversity. We're familiar with these: bacteria, fungi, we've got plant materials, and we've got marine sources. And obviously there are plenty of drugs around from all of these resources available in the commercial domain. The strategies, of course, for these are very different in some respects and very similar in other respects. And again, that becomes another complete topic. What I want to do here, though, is look at some of the basic impacts that artificial intelligence can have in natural products drug discovery. One of them, of course, is looking at the common structural motifs that are present in existing drugs, whether those are synthetics or whether they're natural drugs, looking for common structural motifs and looking at those in terms of big data systems that relate to natural product structures. And we recognize that there's about 200,000 of those now in Dictionary of Natural Compounds. We're looking at AI to help us with structural elucidation, to look for common factors in spectra, whether those are mass spec or NMR spectra, whatever they are, to help us with structural elucidation, with the dream, of course, of automating structural elucidation. Looking at protein binding assessments. And again, we've got systems now that can do this at a very high level based on the X-ray structures and the conformations of natural products. And then looking at the metabolic pathways and looking at that in terms of how do we, if there's a bioactive compound, how do we focus on that compound or those compounds and look for derivatives and look to optimize the metabolism of an organism in order to optimize the production of a bioactive compound. All again for the purposes of some form of drug discovery or bioactive compound identification with respect to a traditional medicine phytotherapeutical. So machine learning here becomes critical because what we're trying to do here is to use the accumulated data, whether that's from ancient texts, whether it's from herbarium information, whether it's structure information, et cetera, putting that data together and using it in terms of machine learning algorithms for the specific purpose, for the specific maybe disease state, for the specific utilization that we imagine for our bioactive compound, and then coming up with a particular bioactive natural product based on recommendations from machine learning with respect to potential sourcing or potential known compounds that might have a specific activity. And there's a very, very good article that's published in Natural Product Reports by Zheng et al. Just this year looking at this whole issue. One of the problems, of course, is this first step, because typically that's missing. We don't have this information readily available in a system of information databases that are linked. So it's very difficult, very challenging to be able to put this information together. We talked about this just very recently. Dr. Daly and myself, we talked about this article published in Molecules with respect to alkaloids and with respect to drug discovery for alkaloids, particularly for multi-drug resistance and for rare and neglected tropical diseases. So looking at global disease needs, we looked at some of the aspects of big data and analytics, machine learning, the utilization of autonomous robots for certain steps in the discovery process, and the chemical, biological systems and the networking. So I'm not going to go through this in any detail. It's available online, so I would suggest you take a look at it. It's quite a substantial and detailed article to approach what might be future strategies with respect to drug discovery. Another aspect of drug discovery, of course, is drug delivery. And we've got all these natural products. This is just a big mess of natural products here. But one of the important aspects that's come into the fore recently, of course, is the ability to use nanotechnologies in various forms, and some of them are listed here, lipid sugar carriers, mesoporous silica, et cetera, in order to change the way that a drug is delivered. And I was recently involved in an article looking at the development of carbon nanotubes in dentistry and the delivery of biologically active natural products through nanotubes, and what they might be used for in terms of various procedures in dentistry, in dental treatments. So the applications here go beyond maybe some of the things that we've imagined. And of course, the same thing applies not just in dentistry, but also in cosmetics. And there's another article that's out in that area. 3D printing, additive printing. All kinds of devices are available on the market. How is that going to be used in drug discovery? One of them, of course, is the development of equipment, moving away from this notion of glassware to ware that you specifically create and reuse for very specific purposes that you design and prepare in your laboratory. So in other words, this is something that sits on the side of your lab and you create the reactionware. You can incorporate chemical reagents into some of these devices. You can incorporate enzymes and biosensors. And of course, you can develop microfluidic devices, and there are special pieces of equipment that will allow you to do that for specific processing needs, you know, for detection and so on and so forth. I'm not going to go into all the utilization. The point is that here we have a system where within the laboratory, within the research group, or in collaboration with bioengineering, that systems can be developed that are very very localized and very specific for the needs that the laboratory has for particular chemicals, for particular enzymes, et cetera, et cetera, et cetera. So it becomes a very interesting adjunct to the way that we proceed in the laboratory. An extension of this is to the development of chemical reactors for drug synthesis. So if we imagine a reaction sequence down here with maybe 3 or 4 steps involved, the question is, can we put together a system that has the reaction parameters, the synthetic operations needed, and develop bioreactors, not bioreactors, chemical reactors that will conduct these various steps, including the purification steps at each chemical step, and so you end up with a flow reactor which is designed and ends up with a final product. So this is what's going on now. This is a way of the future, and again, this was reviewed earlier this year. What are the implications of a system like this that we can put together maybe for extraction of alkaloids, so that the product coming out of a system like this is actually a basic alkaloid fraction that can be processed, or some other fraction, maybe a terpenoid fraction, or an acid fraction, or a basic fraction, whatever. Now let me go to the first word in the title of this: cyber, eco, ethno, pharmacolomics. Cyber, big data analytics; eco, environment; ethnopharmacology, come back to that; and the omics part. What's the cyber part? Well, the cyber part is the data acquisition, the analysis, and the access. And access to data is critical. Access to information, as well as acquiring the information, we need to be able to access globally. And one of the challenges that we have globally, as I'm sure everybody who's listening knows, is access to the literature, global access to the literature that we need. And again, that's big discussion. Organism identification. And again, we're looking, if we're looking with PCR systems, we're looking at database systems and how that relates to known systems that have been studied before, and accumulating all the time the PCR data, the the DNA data for particular organisms so that they can be identified in the future. And that's a massive undertaking, and it's going to be critical in the future in terms as we look at the identification of an organism in different parts of the world. The ability to be able to do that online, for example. Artificial intelligence and machine learning for spectral interpretation, structural elucidation, synthesis, and metabolite networking. So all of these are database systems that relate to how we do the chemical aspects of natural product work in the future. Process automation and robotics. This relates probably more to biological evaluation and testing. The ability, because this is what's routine in industry now. Routine robotic analysis of compounds, actually doing the chemistry of them as well, but process automation in terms of the biological response through robotics. So testing and analysis, data interpretation is all done by robotics and computerization. The last term I'm going to bring up is blockchain technology. And some of you will have been exposed to that term, others of you may not. That's going to be the final part of the presentation, because I think that in the future, that's going to transform quality control for traditional medicines and phytotherapeutics. So integrated data systems, this is a dream. And it's a dream that Jean-Luc Wolfender and some of his colleagues and myself put together back in 2018. And it involves a portal with all kinds of data systems, not data systems in a single location, but interactive data systems across the world. And it includes all the aspects that you might want to think of, whether it's the genomic data, the biochemical data, taxonomic data, chemical data, bioactivity data, et cetera, et cetera. So all this would be accessible, hopefully on your smartphone. That's the dream, to put everything available for everybody as an open access portal that would be available for data entry and curation, not just data exit. Another aspects of the cyber, of course, are remote sensing, and we'll come back to that in a few moments. AI and machine learning for bioactives. We've talked a little bit about that in terms of structures that are important and how they relate, and what we can learn about structures in terms of bioactivity over the period of time when we compare them with hundreds of thousands of compounds. Looking at AI systems and machine learning systems for retrosynthetic analysis and retrobiosynthetic analysis in terms of effective synthetic procedures, ones that are going to work, ones that have a high probability of work, and ones in terms of biosynthesis that provide a rationale for how natural products are made. And again, we've talked about this issue a little bit, this global natural product information access. Absolutely critical that everybody around the world has equal access to global natural products information, whatever that happens to be. And again, big topic, huge topic. Key though, of course, is how we translate the results to society. And one of another big topic, of course, is that this change of how results are translated to society has been dramatic. Excuse me, since COVID, because now we're seeing results in the media before they've been peer reviewed, right? So that the peer review process, which of course has been our standard, is now blown out the window because the results are there. So even just today, we're dealing with new results with respect to booster shots and what that means in terms of injections for society. The eco part. Many years ago, I invented this term, ecopharmacognosy, and it was to bring issues of sustainable research philosophies, programs, and laboratory practices to pharmacognosy. That has not changed. That need has not changed. We still need to be thinking in terms of what we work on and why and how with respect to sustainability for the future. We can't be working on drugs that are not going to be sustainable. We simply can't. That's not a productive use of funds or time. We need to be looking at the impact of climate change, because climate change is going to change many aspects of where medicinal plants are grown and the compounds that are within them, because the metabolite profile is likely to change. We don't know how, but it's likely to change in terms of drought, in terms of heat, in terms of additional rainfall, in terms of salinity, if you're growing medicinal plants close to a rising sea. In addition, we've got the eco part is looking for natural product diversity in new sources, whether those are various forms of extremophiles and endophytes, etc. And that's been going on for quite a while, but it has to continue. Because just in terms of the endophytes within a plant, the opportunities are enormous, because it's an enormous number of fungi and bacteria that are present in medicinal plants that need to be investigated in terms of explaining whether they might even be responsible for some of the biological activity. The collection of ethnopharmacologic information under the CBD and Nagoya protocols as translated locally to particular countries. The processing and analyzing of that information, there's a lot of information there that is global information on a plant. So relying on the information that comes from a particular system, whether that's the Chinese system or the Ayurvedic system or a Malaysian system or a Thai system or whatever it happens to be, is not enough, because that plant may have other uses in other parts of the world and be used in other systems. And there may be other information in it. So processing and analyzing global information becomes key in terms of SIPO. Prioritizing unbiased research. Unbiased. What do I mean by that? I mean, we're not validating traditional medicine use here. That's not what we're doing. We're exploring it. We're examining it. Validating is putting a bias. It's saying that everything that went before is okay, and we're just going to go in there and we're going to prove it right. No, that's not what science is about. Science comes into research like that from an unbiased perspective and says, here's the experiments, we're going to do the experiments, and we're going to see what happens. And we'll see if it supports or maybe it doesn't support. The pharmacology. What is being tested? Is it stable? How is it being analyzed and standardized? So it's looking at that particular issue for biologically active compounds, because we need to know in any pharmacological test or any biological test what's being tested and is it stable. In other words, a chemist, phytochemist, gives a compound to a particular biologist, and the biologist puts it in a fridge and a month later tests it. Do we know that it's the same material that was given by the chemist or the phytochemist? Reproducibility. One of the challenges that natural products biological evaluation has had over the years is reproducibility, a very fundamental aspect that we need to pay much closer attention to. Network pharmacology, the impact of individual compounds or mixtures, standardized mixtures on a genome. Which genes are upregulated, which genes are downregulated? What does that mean? What does that mean in terms of biological activity? What does it mean in terms of toxicity? What does it mean in terms of synergy and antagonism, for example? Another very underdeveloped aspect of medicinal plant research. It's very difficult to do. Also, in terms of ecopharmacognosy and in terms of sustainability, we have to look at the rationalization of unsustainable complex natural products. Because if you've got a 50 component mixture, that's not a sustainable mixture of plant materials. At the same time, beware of pains and IMPs. Pains are pan-assay interference compounds, invalid metabolic panaceas. Compounds that are all over the place in the plant natural product world and interact with a wide range of bioassays. And here's some classics: quercetin and a whole bunch of flavonoids, camphorol, etc., etc., gossypol, and azelaic acid. Azelaic acid is all over the place, almost ubiquitous, and has many different biological activities. The key here is none of these can be used for standardization. Let's go quickly to the omics, taxonomics, genomics, metabolomics, agronomics, economics. Taxonomics, what is the organism? How do we identify that organism? How do we assure that it's been identified authentically? Genomics, what can it produce? And how does it produce that? What are the genes involved? What are the encoded enzymes that are involved in that? Metabolomics, what does it actually produce and when? And also, what can it produce if effort is made to explore that avenue? Agronomics, how can it be grown? When do we harvest? Economics, what's the cost? What's the cost of the product in the marketplace to the patient? So the 4AR, quintuple helix, and traditional medicine quality control. We've looked at some aspects of Industry 4.0. We've looked at the quintuple helix. Many of you have seen this slide before, the 4 pillars of traditional medicine quality control: information systems, botany, chemistry, and biology. That's what we're building on here. And I'm sure that Professor Guo is going to talk a little bit about this in his presentation. It's a holistic approach to quality control standards, and that was published back in 2015. Very, very important in terms of relating this to pharmacopeia standards and trying to harmonize those standards on a global basis, because so many countries around the world use these particular pharmacopoeias. According to WHO, 1 in 10 medicines in developing countries is counterfeit. So the ability to be able to recognize fake medicines is absolutely critical and should be a fundamental aspect of healthcare in a country. And it's worth about $200 billion a year. This is not a trivial industry. Online products and their associated health claims are a global regulatory issue, and we're going to come back to how that might be alleviated. One of the things that's happened recently is that there's a handheld, very simple near-infrared scanner that is linked to artificial intelligence, linked to databases, which you can use to look at tablets and identify the drug in those tablets. Think about extending that to traditional medicines. We've talked about this, characteristics of traditional medicine quality control. It's got to be patient-centered. It has to be patient-centered, and it's based on quality, safety, effectiveness, consistency, and be accessible and prepared in a sustainable manner. Those of you who know me know that I like M&Ms. I just wish, one of my dreams in the world is that traditional medicines would be as consistent around the world as M&Ms. So this puts the patient at the center of the complex, the patient at the center of the industry, science, government, retail practitioner complex that provides a product to the patient. And the patient has to be assured of these quality, safety, efficacy, consistency, accessibility factors based on the interactions of these. So this part here is, again, back to that third, the triple helix concept: collaboration, industry, science, and government. Blockchain technology. Blockchain technology is a distributed ledgering system based on cryptographic systems. What that means is it's open, but it's closed. It's open to viewing, but it's closed in terms of once you put data into the system, it stays, and it can't be changed. It can't be modulated. It can't be modified. So if you think about that in terms of a traditional medicine, what it's doing is it's providing an immutable, an unchangeable public record of each point of movement and financial contact in a production process. But in terms of traditional medicines, we can also, of course, use it in terms of quality control and provide continuous management and verification of those quality control steps. So, for example, if we look at it in terms of a traditional medicine, we can see that in the collection step, we can look at the history, the identity, the sustainability. In the transportation, we look at make sure the identity is assured, contamination is minimized because we're monitoring movements and authentication at every step. If we look at manufacturing, we're looking at the quality controls for botany, chemistry, biology, and the processing, and looking at GMP, good manufacturing processes applied, and continuous quality control for each step in the manufacturing. In terms of the product, we're looking at the product lifetime and the full history for quality control, which reduces the risk for when it goes to the patient and the consumer. So what they're seeing and what they're able to trace is the origin, the operations, the transparency in the time frame from the origin of the plant material right through to the product when it's purchased. Each step is monitored. Each step provides an immutable record, a continuous accumulating record. So what it's doing is it's providing this traceability and transparency from somewhere out in the field and the first collection site right through to a product in the marketplace, from farm to pharmacy. It's already appearing in several countries around the world with respect to fruits and vegetables. In the future, it's going to be applying much more widely to foods, and I believe eventually it will be providing information for patients with respect to traditional medicines. Future directions. Let's try to summarize some of the things that we've talked about here. Expanded and integrated AI and machine learning systems for ethnopharmacology, botany, chemistry, and biology to facilitate bioactive compound discovery and analysis. Enhanced technology integration, automated processing, handheld access to digitized data, and remote sensing. Promoting the sustainability of medicinal plants and their quality, safety, efficacy, consistency, and accessibility, particularly in times of climate change, because that is changing everything. The use of blockchain technology for traceability and quality control for offline and online products. This is the difference. This is the difference, because once you put that stuff online, now it's beyond regulatory control. If you've got blockchain technology, it can be applied to online products as well. For the patient, focus on those pharmacopoeial parameters which reflect quality and activity, not merely the identity of a plant or a marker compound. So there's going to be some rethinking about what goes on with pharmacopoeias as the technology impacts. Again, that's another major discussion. Improved translation of research outcomes to society. What's our relationship in terms of the research we do and the patient? How does that affect traditional medicine patient interactions? And finally, there's the whole area of education that has to change, that the integration of where we're going in the future and enhanced training programs, workshops, and seminars that people all over the world. There was a recent WHO survey that looked at this, but particularly in the region of Asia, which is CRO and WPRO, tremendous demand for training programs, workshops, seminars, not just for practitioners and researchers, but also for regulators, for industry, so they understand the science that's going on in natural product research at the moment and how advanced it is and what it's capable of doing. So here we are, we're at the end. And George Bernard Shaw says, you see things and you say why, but I dream things that never were. And I say, why not? And some of you know what's coming next. My favorite dreamer, who says, the dream you dream alone is only a dream. The dream you dream together is a reality. John Lennon. And he's right. He's right, because we need to be doing this together. We need to be doing natural product research together in a highly collaborative manner where people are working together towards advancing natural products and the impact of natural products for the consumer, for the patient. Thank you very much indeed for your attention. And I'm sorry I went a little bit over time, but it's greatly appreciated. Thank you to the organizing committee for inviting me, and I wish you all safety and health from this horrible, horrible virus. Thank you very much indeed.
Thank you, Professor Cordell, never failing to provide us the big picture on the natural product research, always reminding us more and more of the things that we need to do, and always reminding us of the collaborative needs among the scientists. Thank you again for an amazing lecture. And with that, I think the organizer would like to thank Professor Cordell in our usual manner nowadays, in a modern virtual way.
Thank you. Thank you very much indeed.
Okay, with that, and I'll return this platform to the MC of the day, Dr. Nurul Najah. Thank you very much.
Thank you, Hadiani.
Thank you very much, Professor Emeritus Professor Geoffrey A. Cordell, for your presentation and sharing. And thank you, Professor Dr. Nur Hadiani Ismail, for chairing the session. Ladies and gentlemen, now I would like to invite Emeritus Professor Dr. Muhammad Ikram Muhammad Said to introduce our second plenary speaker and chair the session. Professor Datuk, the screen is yours.
We cannot hear you.
All right.
Yeah.
Good morning. I have to repeat what I've said just now. This morning we heard something from an interesting talk from Jeff Cordell, and it is a continuation of our plenary speakers for ASOMPS. And as compared to the other plenary speaker who have been in ASOMPS for quite some time, they are all veterans of the natural product scene, but this is a young guy, well, considered young. He's not even 60 yet, but not really a new kid on the block. He has done a lot of research on TCM, and just to introduce to you a brief background of Professor Dian Groer. He is presently a director of the Shanghai TCM Research Center, which is this center is in the Shanghai Institute of Materia Medica, which is in the part of the Chinese Academy of Sciences. He's received his PhD in pharmacognosy in Beijing Medical University in 1990. And then after that, he left, he did a 3-year postdoc in Texas Tech University, 1993 to 1996. And of course, his main focus is on TCM, comprehensive analysis and quality standards. But he has a niche in his approach in trying to make quality standards, not only for the Chinese pharmacopoeia, but also for the American and European. I think he was the first scientist to introduce this type of approach in all the pharmacopoeias, not only in China, but also in the US and also in Europe. And the holistic approach is, he called it the Trinity analysis, which is taking into account the chemical, metabolic, and also biological analysis. And this approach has, I think, gained momentum, and he will elaborate on it today in his talk. But other than that, of course, he's also an editor of many journals, I think more than 10 journals related to natural products and TCM. And of course, he has published a lot of papers, almost 1,000 papers now already. And what is more important, I think, is the citation, a lot of citations for his work that has been published, more than 15,000 citations. And of course, he has received awards, not only from China, but also from the International Pharmaceutical Society, for example, from ASP, from ABC. From ASP, he received the Varro Tyler Prize, and then from ABC, he got the Norman Farnsworth Award for excellence in botanical research. So today, Dr. Dian Guo will be, I was just asking him what is the initial SAC, and he said he also don't know what is in front of his name. Strategy and approach to elaborate TCM quality standards. TCM quality standard. Please, Prof. The chair is yours. Platform is yours, sorry.
Okay, thank you very much, the chair, for your kind introduction. Really, for me, it's an honor, and I'm very pleased to be invited by the organizing committee. So it's pity, like everybody, that we could not be physically in the meeting site in Malaysia, which I have been there for years. So, but you know, we have to accustom to this kind of virtual meetings from now on, maybe. But anyway, we hope that we can come back to normal as soon as possible. So let me share my slides. You see, I think you have to, okay. I'm not sure, let me see. This is not my slides. Can you see this? Sorry, can you see the slide?
Not yet.
No, okay. I'm afraid you have to.
You put on the share screen?
Yeah, I have to stop your, okay, right? Okay, I got it. Now you can see it, right? Can you? No? I cannot hear you because you mute.
I can see now.
Yeah,
Oh, okay. Sorry.
No problem.
Okay. All right.
Okay,
Thank
this
you
is the first slide, right?
Yeah, this is my
All
first
right.
slide.
Okay, you're on.
Okay. So today I will focus on the quality issues, the quality standard, and also the quality related research on the traditional Chinese medicine. So the strategies and approaches that we are, using in the past years. Like the chair introduced, I'm from Shanghai. Now I'm in my office. So, well, the challenges, I think just now, Professor Cadell already mentioned that we are facing challenges for the quality control. So due to the increasing demand of the raw materials, so adulteration, falsification, heavy metals, pesticides, also due to industrialization. So this is really widely occurred in many places, not only for TCM. So how to solve this problem? By using the methodologies or technologies to control the quality. So this is definitely the challenge. The second challenge will be the single marker strategy. As we can see from Chinese pharmacopoeia in the past years, I mean, we have 11th edition of the Chinese pharmacopoeia. From the previous 10 editions, we can see majority of the TCM herbs or even the finished products, they just use the single marker assay. So that's definitely not fit for the purpose. So because of TCM, not to say about complex mixtures, but even single herb, they have hundreds or even thousands of the components. So single marker assay is not fit for the quality control of TCM. Thirdly, I mean, that will be a challenge for the science, how to clarify the chemical compositions and even the active components. After all this basic research, how to elaborate the quality standard, which is practical and feasible and also scientific. So this is really the challenge. Well, here I gave you one of the famous examples for ginkgo biloba. This is commonly used, not only in Europe, but also in China. You can see from here that even for this commonly used herb, that's still the adulteration. What is the problem? Here, the ginkgo extract, you can see they use routine for the quantification. And here is the finished product. You can see the routine. Because you only quantify the single marker, I can see that's much higher than other components. But
Excuse me, Prof.
Yeah.
Can you change the slide display, because now it's currently show the presenter view, not the presentation.
This, can you see the slide now?
It's like two slides in one screen.
Oh, okay. I have to probably.
Yeah, it's setting something.
Okay. Probably I have two screens. Let me shut down one screen.
Thank you, Prof.
Sorry about it. Now it's better.
Yeah, now it's clear. All right, thank you.
I have two screens on my desk, so
okay. Thank you very much.
Okay, thank you. Here you can see that this is one product in the middle, the chromatogram. On the bottom, you can see that's much clear. Only routine, now has been jumped up. So that's the intentional adulteration. So what's the problem? That's clearly the quality standard problem. If you only control one single marker, that they will intentionally adulterate that. But if you monitor the entire profile, that will not allow this type of the things happen. So that is exactly what the challenge. So based on this, then what we adopt the strategy, we call it 3-tier strategy. That means we have to deal with the basic research first. That means quality-oriented basic research. We develop the trinity analysis, by combining chemistry, metabolism, and so on, and to clarify the chemical components. Second, we have to develop the holistic quality standard, as mentioned by Professor Cadell. So based on the basic research, and this quality standard must be useful to control the quality. And then that's not enough. This quality standard sometimes still cannot serve the purpose to control the quality, to evaluate the quality. So third-party testing, that is also very important. So based on this 3 tiers kind of strategy, then we can really control the quality. We are now practicing this strategy, and we found this very useful. We had the platforms on the national level, and of course, now we are in pretty well-equipped labs. So first, let me focus on the TCM quality-oriented basic research. Here, I developed the kind of idea that based on the comprehensive research, and then you come up with the feasible standard. What I call it feasible, that means must be practical. Otherwise, if you really quantify over 30 compounds in one chromatogram, that will not be practical, will not be used by the daily testing. Therefore, we have to, based on this, and come up with a feasible standard. So this part, usually you won't see it. It's only on the quality standard you can see it. So that's usually recorded in a pharmacopoeia or other national or provincial standards. So this part, but this basic research is the fundamental basis. So Professor Cadell and I co-published this paper. We depict this whole strategy. So for the basic research, what we are focusing on, I think we have to integrate chemistry, metabolism, biology. By combining these 3 strategies or 3 aspects, then we come up with the final clarification of the markers for the quality. So you have to really find out what are the components which is meaningful or significant for the quality control. So this is based on this type of the research, dubbed trinity analysis. So firstly, well, let me focus on the chemical analysis. So chemistry always the basis. So now, thanks to the hyphenate technology, RCMS, LCMR, and other technologies, so we can really dramatically enhance the overall profiling, capability. So before we only identify maybe tens or several, 30 or 40, that's already a lot. But nowadays, like a ginseng cases, we could really characterize over 2,000 compounds, even for the finished product, composite, compound formula. That's also we can identify or characterize a lot of compounds. So the capacity for the profiling dramatically increased. Secondly, metabolism. Why do we do metabolism studies? In my opinion, I think that is really the basis for the clarification of the active components. After you feed or administer to the human body or animals with extract fractions or compounds, then you will see what are the compounds has been absorbed and distributed and found out the in vivo process. By using metabolic fingerprinting technologies, then you can clarify that what are the components that can be absorbed. Only those components that be possibly the potential active components. So this type of study also is important. Thirdly, will be by using biology technologies. So either animal model, cellular model, molecular model, whatever that you can use, and even the genomics, various system biology technologies, then we can confirm what are the effective compounds in the herbs. So based on these three types of studies, then finally we can come to a conclusion that what are the significant components that we can use for the quality standard control. Okay, let me give you a few examples. A ginseng switch, which I like most, because ginseng, red ginseng, American ginseng, noto ginseng, this is the same species, same genus species, which widely used in the daily practices. So therefore, they all contain saponins, ginseng saponins, and they are very similar. So therefore, there are adulterations because price-wise, they are very different. American ginseng is much more expensive in the Asian ginseng. So sometimes they use Asian ginseng to adulterate an American ginseng. And even for the same species, like ginseng, they use the airy parts or mixed extracted kind of material from the leaves, stems, they adulterate into the roots. So this is very important that we can use the hyphenated technology that to clarify, to differentiate the different species. Here is the overall profiling of the ginseng species. We can see they are very similar, but there are some minor differences. With this, we still cannot differentiate the different species. And then we go further deep into the chemical components. So like a saponin identification from the different species. And at the beginning, we could characterize over 600 different saponins and with a lot of new compound, definitely, but with this hyphenate technology. And then we focus on the airy parts of the ginseng materials and like leaves, stems. The purpose for this, as I said, we want to know that what are the differences in overall profiling for the chemical, for the saponins. So therefore, we can, based on this, and to differentiate any adulteration from the airy parts. So here we can see that based on the chemical components, by using PCA, analysis, chemometric analysis, we can basically fractionate it, the different part of the ginseng, leaves, roots, or flower buds, or berries. So based on these 13 markers. So this is just the basic kind of differentiation. Further, we want to know that to what extent of the adulteration that we can differentiate by using this technology. Therefore, we artificially mixed the two parts with the leaf, the roots, 10%, 90%, and all the way to other way around. So finally, we found out that with 10% or above of the leaf adulteration, we can easily to discriminate all the differences, whether or not they are adulterated. But any samples mixed with lower than 10%, we do not have the quite confidence that to differentiate. But that's clearly show that if they are intentionally adulterate, that we can differentiate this different types, different parts of the materials. So for noto ginseng, it's another species even more popular in China than ginseng. So this is also the very, very important TCM herb, Panax noto ginseng. So we focus on the leaves or area parts, and we try to also clarify the chemical components first. So here is the comprehensive analysis of noto ginseng leaves. Here you can see that only from the leaves, more than 900 saponins has been characterized. And by using this approach, we dramatically increase the capacity for the characterization. So, and afterwards, we definitely have to isolate, because only by our CMS, we won't acquire the chemical compounds. So through isolation, traditional conventional methodology, that we can obtain this type of the compound, and definitely a lot of new compounds. And by using that, also we can differentiate any adulterations from the marketed samples. Here we acquire all different samples from the drugstores. Here you can see that there are really no fixed products, purely different from noto ginseng. But here you can see that lower part, that's much, much lower concentration than this normal kind of samples. That clearly shows that they may adulterate with the error parts, or they just use much, much less the authentic samples in this, samples. But, with this, then we also can differentiate this lower quality or substandard quality powders of noto ginseng. So, and after all these detailed studies, we have developed a much better chromatogram, which can isolate, which can separate all the different saponins from the different species, and with a very short time by using UPLC. So I'm sorry that this is UPLC. This is normal HPLC, but this is UPLC with 15 minutes. Traditionally, they only use HPLC that takes more than 70 minutes for one assay. So therefore, we modernize the USP quality standard for ginseng, American ginseng, and also noto ginseng by using UPLC methodology. Here, we use much, much shorter time. So finally, USP take this 15 minutes one, which is much better separation than 10 minutes. 10 minutes, even you can achieve the methodology validation, but it's lower in the separation. We have to sacrifice, the separation. So this is the one case. Second case I like to go through quickly for the alisma. Alismatis rhizoma. This is also a commonly used TCM herb. There are two species here. In 2015 edition of Chinese Pharmacopoeia, only this species has been recorded, Alisma orientale. So, but when we do the market investigation, we found that a lot of this species has been marketed, Platago aquatica. So what is the real situation? So therefore, we choose this, herb for the detailed study. And firstly, definitely we use the same technology to identify the chemical components. Totally, we isolate over 21 novel triterpenoids, and with also some new subsequent terpenes. And afterwards, so we identified the structure. Definitely, there are some new structures you can see here with this ring. And after that, we try to use the approach to target it for the profiling for the different species of triterpenoid from Alisma. And of course, I want to go to details about overall profiling and sensitivity, selectivity. The methodology we definitely will have to manipulate with this techniques and try to increase sensitivity and selectivity. And finally, we can identify over 473 triterpenoids. Here you can see the two species co-share a lot of common triterpenoids. That's different from other species. Sometimes they are very different, but here the two species shows quite similar, but still they have their unique triterpenoids. This shows the structure types of these different triterpenoids. And then we try to use metabolomics-based comparison and differentiation of the two species. Based on the markers we identified, so we can easily to do the PCA analysis to differentiate these two species. They are quite, well separated into two groups. And this shows that, this method can differentiate this two species. And then we collected the market samples of 22 batches. And finally, based on the previous results, as I said, we can differentiate easily and correctly, precisely about the different species of these two. And we found out that 21 batches of the sample among 22 samples are the species of this one. Let me see, it's the unofficial species, Plantago. So this is really the problem. After we do this study, I really reflected this to the Chinese Pharmacopoeia Commission. I think this is wrong. Based on this standard, the market sampled all the unofficial species. That's illegal. So based on our study, they are quite similar in chemical components, and also our pharmacological studies also show the two species share a lot of common, activities. So therefore, we recommended to the Chinese Pharmacopoeia, so still adopted these two species as we recover to the 1977 edition. At that time, it's two species, but I don't know why later editions, they dismiss the one species, which is the dominant species, Plantago. So now in new edition of Chinese Pharmacopoeia, 2020, that's two species officially adopted. So for the third species, which Cordyceps. Cordyceps, maybe you know this one. This involves two parts, insects and fungus. This species, this herb is very, very expensive. Probably, more than the gold, more than 200,000 yuan for 1 kilo. That's really expensive. Therefore, adulteration is widely, existed. So we collected 97 batches of the authentic sample and also the possibly fake samples. So with this 97 samples, we try to use different methods to differentiate all these fake products from the authentic ones. So originally in Chinese Pharmacopoeia, is only focused on the nucleosides or amino acids, which commonly occur to all species almost. So therefore, we turn to peptides. Firstly, dipeptides. We can see that from the species, that overall profiling of the dipeptides, you can see that they're quite abundant. So therefore, we focus on this by using also the RCMS technology and also through the reference standard identification. So totally, we could identify over 170 dipeptides from cordyceps, and majority of this are composed of 19 different amino acids. but without cysteine. So this is a really unique feature. All these dipeptides, we do not find any cysteine in the dipeptides. So majority of them are leucine, proline, and valine. So here we try to, whether we can use this dipeptide-based differentiation from, of cordyceps, authentic cordyceps from the different origins or the fake products. Here shows the two groups of the authentic samples. Why they divided in two groups? Because the one is from the wild, another one is cultivated. Because now Chinese company, one of the company successfully cultivate this cordyceps. So they share a lot of common features, but there's still some differences. We can differentiate them. All these are the fake products. So from this dipeptide-based differentiation, we can easily differentiate all the authentic ones and with the fake products. Here shows the authentic ones. And of course, from this also different plotting, PC, HC, or thermal plottings, also we can easily, differentiate the cultivated and the wild from the adulterated. And here, HCA analysis also can differentiate with the fake products. So that shows that dipeptides could be used as markers for the differentiation or the quality evaluation. Maybe we are still in the process. So other than dipeptides, we want to know that whether polypeptides or natural polypeptide in cordyceps will still be useful, not only for the differentiation, but also for the quality evaluation. So we now still doing this research, and we found that, quite abundant of polypeptides in this cordyceps. Here also we can see that the fake cordyceps with the authentic cordyceps, they can be divided into two groups. And we focus on 18 differential polypeptides, including peptide 1, then to use this to differentiate all the authentic ones, and of course, the fixed products. So this 18 natural differential polypeptides, we identify already one, peptide we synthesize with the 12 amino acid sequence. Here, the sequence of this peptides. So other 17, we're still in the process to identify them, also synthesize them. So here we can see that this peptide 1, that we can find out that is only in the wild and cultivate one. So all other faked products or faked cordyceps won't contain this peptide. And we can see that definitely is a marker for authentic cordyceps. So both species, that means not species, but both samples, wild and cultivated one, contain this. So this is definitely clearly is a quality marker for the differentiation. So here we want to see whether or not this peptide 1 are from the insect or the fungus. So after the study or investigation, we found out that this peptide 1 only exists in the fungus, not in the insects. So therefore, we now made it clear that the origin of this peptides. So hopefully, we are now identifying other peptides and also testing their biological activity. Maybe they can contribute this, the detailed kind of pharmacological activity rather than focus on the nucleosides, which commonly occur in all the animal species. So those are the basic research. Second part, as I said in the beginning, we want to construct the quality standard, which must be holistic, which not only focus on the single marker, but definitely you got to consider overall profiling. Here is the strategy or the model of holistic quality control, here including the conventional quality control method. Not meaning that we're using fingerprint or multi-marker assays, we don't need this conventional quality control method. But other than that, we definitely need this microscopical TLC. All this is still very useful for the quality control, but that's not enough. Fingerprint analysis, multi-marker assays, like I said, in the case of ginkgo. So this really to monitor the quality and evaluate the overall profiling. Then we can differentiate the really good quality from the substandard or low quality samples. So here is some of the methodology. Everybody knows that, TLC, HPTLC, widely used in all pharmacopoeias. This is the 4 species I mentioned. Also, we can use TLC to differentiate them, but definitely we can use other methodologies for the even adulteration. So here's HPLC fingerprint. This is, of course, very, very useful, and now it's widely used. And even in the Chinese pharmacopoeia, we adopted this fingerprint technology. This is for Chinese salvia. You can see that this is the standard, this is the raw material, and this is the finished product. So we can easily monitor overall. But before, it was only monitor this single compounds. So intentional adulteration is possible. And of course, this is a method that's using one standard to quantify multi-markers. The reason for this is that because of the markers or the quality standard, we know that the reference standard is very expensive. If we want to quantify this 5, peaks, then we need to use this 5 reference standard. So this is really requires the high cost and also the availability. I mean, that's also the problem. So we developed this method by using single marker to quantify the multi-markers. So this requires the conversion factors. So how to evaluate, this whole system to get the precise conversion factor. So we published a lot of papers on this, and now is widely adopted this method in USP, CHP, and also European pharmacopoeia. So here, we developed some of the quality standard for the USP. Now we are still in the process for the ginseng series, ginseng, not ginseng, red ginseng. This now has been adopted by USP. And of course, for EP, then we also now working from these several herbs. The first one is Ancaria, which has been adopted in 2014. So now we have developed over 20 different herbs submitted to EU, European Pharmacopoeia Commission. And here's the progress. So we have developed 15 quality monographs of 15 TCM herbs and now have been adopted by USP. So, but there are over 20 more monographs have been developed, but they're still in the process for evaluation. Totally 18 TCM quality monographs have been adopted by European Pharmacopoeia. So we are now actively participating in this process. And next month we'll have the, also the virtual meeting for the experts to evaluate the monographs submitted from the different parties. So Salvia and Ancaria. So this is total 18. So, but the Chinese scientists involved only from 2014. So now we're still in the process to develop quality monographs. Well, for the future, I think this has been mentioned by Professor Cadell already. We share almost the same idea. So quality standard definitely is necessary, important, but that's definitely not enough. Only by the quality standard, you cannot get to good quality products. So you have to trace back to the origin, to the original planting stage for the seed, even the seed or the seedling. This quality also important. Like agriculture crops, if you don't have a good seed, you won't get the good crop. So, or the productivity. So for herbs, the same thing, quality of the seedling, the entire supply chain. After that, TCM involved in not only the crude drugs, but also, some later stages. But this crude drug stage, the GAP involved, and also the preliminary processing also is important. So how to process the raw material, the fresh material also matters. So after that, the SOP of the process. As you know that the TCM, there's a special thing is the processing, 泡制. So 泡制, which really matters. I mean, how to do the SOP of the processing. This has become the critical process. So therefore, this part, I think, is very, very important for the processing, decoction slices. So this also important. But the later part definitely will be the manufacturing, the GMP process, also to follow the standard. Like Professor Cadell mentioned, M&M, or even coffee, even red wine, those type of the quality is very consistent. If our herbs or traditional medicines can follow that kind of protocol, definitely we can achieve that goal. I mean, that's possible. We already have a model that we can follow. But for the TCM herbs, that definitely will be more complicated. So after that, of course, let's come up with the quality standard for the finished products. This is only at the last stage, finished products. But all these previous steps, not limited to these 4 steps, but definitely there are other steps that matters. So we have to really consider this all steps, all stages, and control the process, control the stages. So finally, we can definitely to get the qualified or the quality products that's to meet the demand, to meet the clinical requirements. So good thing is that Chinese government invested a lot of money for this 5-step process, quality control of TCM herbs, which I'm one of the chair, I'm the director and the chairman of this scientist group to monitor the whole processing. So we are now still in the 14th 5-year plan. We'll continue this process. So, and with all these studies and the quality standard or quality control of the TCM herbs, then I hope that we can achieve the goal that to meet the clinical and medical society demand. So with that, I'd like to thank all your kind attention. Thank you very much for your attention.
Thank you, Prof. Go. Very interesting talk. I think now maybe we can use this as a model for Malaysia as well, because we also have a traditional medicine industry based on Malaysian plants. Once again, on behalf of ASOMPS committee, I would like to thank Professor Dian Guo for his excellent talk, and hopefully we will be able to see him soon once this pandemic is over, but we can never tell. So hopefully we will meet again in a different platform, but I hope you had good memories of the ASOMPS in Kuala Lumpur. You imagine that yourself, you are in Kuala Lumpur in my office, for example. All right. So we'll meet again. Thank you very much.
Thank you. Thank you very much.
There's a certificate of appreciation for you as a plenary speaker from the organizers.
Okay.
Okay. So I think they will take a photo of us and they'll pass it on to you.
Okay, thank you.
Okay, thank you. Now
I will stop the co-sharing. Okay.
Oh yeah. Okay.
Okay.
All right.
Thank you.
Okay. All right.
Thank you very much, Professor Dr. Dian Guo, for your presentation and sharing session. Okay, and thank you, Emeritus Professor Dr. Muhammad Ikram Muhammad Said, for chairing the session.
You're welcome.
Ladies and gentlemen, the time has finally come for our concurrent sessions. Before that, I would like to invite all participants to watch Flash Poster Presentation 5 for about 30 minutes, followed by a coffee break at your own pace. Please join us again at 10:50 a.m. for the invited speakers session in 2 backup rooms. And you can find the link at the agenda menu and scroll to invited lecture hall C or D. Flash presentation 6 and 7 will be played during the lunch break, and please join us again at 2 p.m. for concurrent session 2A until 2F. Thank you for your attention. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh.
Naja, let's take a picture.
The title of my poster presentation is Isolation of a Gas.
Done, Naja?
Got it?
I think so, yeah. Okay, I think so, because they're on different platform.
Okay.
All right.
Okay.
All right.
Thank you very much. See you
All right.
soon.
Thank you, everybody.
Thank you.
Please stay
Thank
tuned.
you. Nice lecture, Dion. Nice,
Okay,
really
thank you.
nice.
Thank
Really
you, Jeff.
My pleasure.
Okay.
The title of my poster presentation is Isolation of a Gastroperoxide and Linoleic Acid from the Edible Mushroom Sisophyllum commune using centrifugal partitioning chromatography. A gastroperoxide is an important bioactive compound previously isolated from Sisophyllum commune, while linoleic acid is a polyunsaturated fatty acid that has cholesterol-lowering, antimicrobial, and antiviral properties. Although a commonly reported fatty acids in mushroom, linoleic acid has not been isolated from Sisophyllum commune. This study is therefore aimed to develop a simple and fast method for the isolation of both compounds using centrifugal partitioning chromatography. Firstly, an ethanolic extract of Sisophyllum commune was prepared and then enriched by liquid-liquid partitioning with hexene. The partitioning coefficient, or KD values, of targeted compounds in the hem-wet biphasic solvent system was estimated using the shake flask method, and the results are shown in Table 1. Linoleic acid had a KD value of 2.82, while a gastroperoxide has a KD value of 0.7 in Arizona V solvent system. And the separation factors were 4.02, and therefore Arizona V was selected for the CPC separation. Fractionation of the enriched extract was performed on Armand CPC system, and the fractions were monitored on HPTLC as shown in the results section. Bands with similar retention factors were combined, and the results shown that the linoleic acid yield was 16.6 mg and the gastroperoxide was 6.5 mg. The compounds were further identified using LCMS analysis coupled to a PDA detector. Linoleic acid showed a retention time at 10.10 minutes, while the mass was the protonated form at M/Z 2.81, corresponding to the linoleic acid. The purity was estimated to be 80.64%. The gastroperoxide, on the other hand, had a retention time at 15 minutes. The M/Z values of 395 corresponded to the protonated form with a loss of hydrogen peroxide. The purity was found to be 84.97%. In summary, CPC purification of hexane-enriched extract can be used to isolate peroxide and linoleic acid in a single run. However, further purification was required for higher purity.
Assalamualaikum and good day to all participants. My name is Siti Awanis Abdullah, a postgraduate student from UTM Johor Bahru. Today I would like to present my poster presentation entitled Isolation Antioxidant and Alpha Glucosidase Inhibitory Activity of Cesium graphite. So now I proceed to the introduction parts. The Myrtaceae is the major group of flowering plants, comprise about 100 genera and 3,000 species. In Malaysia, Myrtaceae included about 9 genera and 210 species. So the Cesium plant were reported to have many phenolic compound and also proved to have high total phenolic content with significant antioxidant activity. So for the method parts, the powder sample were extract using normal extraction method to get 3 different extract. So the crude extract will proceed for their purification and isolation using different chromatographic technique such as TLC, VLC and CC. And then the structure of pure compound were analyzed using spectroscopy analysis, which is NMR, IR, MS, and comparison with previous study to confirm the name and the structure of pure compound. And then the methanol crude extract were analyzed for their bioassay analysis. First is antioxidant activity using 3 different assays. One is the PPH free radical scavenging. Second is ferric reducing antioxidant potential (FRAP). Third is ABTS assay. And next, the crude extract were tested for their alpha glucosidase inhibitory activity. So from this study, I'm able to isolate 1 flavonoid, which is spinosambrin, and 5 terpenoid. For the antioxidant and alpha glucosidase inhibitory activity results, the methanol crude extracts show good DPPH scavenging activity with the percentage inhibition more than 70% at 100 ppm. So the extract also exhibit good FRAP activity and also showed excellent antioxidant activity with the SC50 value of 145.50 millimolar for ABTS assay. And then for alpha glucosidase activity, the tweets of Cesium graphite demonstrate potential inhibitory assay with the IC50 value of 8.95 ppm. So that's all for my presentation. Thank you.
Hello, I am Dr. Nurviki from UiTM Shah Alam, and I'm going to present a poster entitled Goniothalamus lanceolatin A to H, new bisterolactones from Goniothalamus lanceolatus. Goniothalamus lanceolatus is an endemic plant from Sarawak. It is an ethnomedicinal plant because the natives use it for several illnesses such as treating cancer, fever, and postpartum treatment. Despite the ethnomedicinal properties, this plant has never been studied. Hence, it triggered our interest to look into its phytochemical and biological aspect, not only to rationalize the traditional usage, but also to gain some insight on its safety. We started this study with the question, is this plant really has an anti-cancer properties? So the work started with extraction of the dried ground stem bark and root using hexane, followed by dichloromethane and methanol. All the crude extracts were screened against lung and colorectal cancer cell lines. The results showed that dichloromethane crude extracts gave promising results. So fractionation was done on the crude extracts using MPLC, and isolation and purification of pure compounds were done using preparative HPLC and recycling HPLC. The pure compounds were evaluated for their cytotoxicity against lung and colorectal cancer cell lines. The molecular docking analysis were done on the most cytotoxic compounds. From the phytochemical analysis, 8 new bisterolactones were isolated, namely Goniothalamus A to H. The compounds are deemed rare because they possess a 6S configuration alpha beta unsaturated delta lactone moiety, which typically exists as 6R configuration. Absolute structures were established through extensive 1D and 2D NMR data analysis in combination with electronic dichroism data. Guanylan solatin B and D showed cytotoxicity with IC50 values ranging from 2.3 to 4.2 micromolar and were inactive towards human non-cancerous lung and colorectal cells. Both compounds inhibit EGFRTK and CDK2 by forming hydrogen bonding with important amino acids. Based on the findings, guanylan solatin B and D are potential inhibitors for EGFRTK and CDK2 and may be potent anti-lung cancer and anti-colorectal cancer agents. As a conclusion, the promising findings from this study may support further exploration of the cytotoxicity of beta-lactones from a mechanistic perspective. Thank you very much.
Hello, my name is Abhirami and I'll be presenting a part of my research work on a novel herbal product called ABPA. In 2019, the International Diabetes Foundation reported that 1 in 5 adults have type 2 diabetes in Malaysia. It is characterized by a prolonged increase in the blood sugar levels and it's infamous for its long-term complications that can be fatal if the treatment is not efficacious. Although there are numerous anti-diabetic drugs, these drugs have been reported to cause multiple adverse effects, indicating that they are not safe. Hence, natural products such as herbal medicines serve as an adjunct therapy in the management of type 2 diabetes. ABPA is a combination of several herbal plants, all of which have been reported to be powerful anti-diabetic agents individually. The objectives of this study are to investigate the in vitro antioxidant and anti-diabetic properties of ABPA, along with its glucose uptake mechanism through the activation of both major proteins of the insulin-independent pathway, the P38 MAPK and GLUT4 proteins. For the antioxidant studies, DPPH, lipid peroxidation, and ion chelating assays were conducted, while in the anti-diabetic studies, the inhibition assays of both alpha amylase and alpha glucosidase were conducted respectively. In the cell culture studies, differentiated L6 myotubes were used to perform various treatments of ABPA and metformin as the positive control before commencing the glucose uptake assay. Lastly, ELISA analysis was conducted to determine the concentrations of P38 MAPK and GLUT4 proteins in these cells. Based on the results of both antioxidant and anti-diabetic studies, it was observed that ABPA showed strong antioxidant and anti-diabetic properties at concentrations of 500, 750 and 1000 microgram per ml. The cell culture results showed that ABPA-treated cells increased glucose uptake with increasing concentrations. This was further confirmed in the ELISA analysis of both P38-MAPK and GLUT4. In a nutshell, the study met all its objectives, where ABPA exhibited strong in vitro antioxidant and antidiabetic properties, as well as increased glucose uptake through the activation of P38-MAPK and GLUT4 proteins of the insulin-independent pathway. Thank you very much.
My name is Nadira binti Abdullah. I'm a PhD student from the UiTM. Today I would like to present a poster presentation entitled The Replications of Leaf Dichloromethan Extract in Goniothalamus lanceolatus using a UHPLC ASI Orbitrap High Resolution mass spec. Dengue fever has been a major concern around the world, and currently there is no specific treatment and vaccine to combat this disease. Goniothalamus lanceolatus is an endemic plant from the jungle of the Sarawak and is used by the native people to treat fever, cancer, and also is used as an insect repellent. This plant was reported consist of sterolactone, astogenins, and alkaloid derivative. Currently, there is no published data on the possible anti-dengue virus activity of plant extract from this plant. Therefore, in this study, we are interested to replicate the most potential good extract based on the screening test against dengue virus. Screening of anti-dengue activity through a golden method called a plot assay at a single dose concentration, which is a 50 microgram per ml, show that leaf dichloromethan exhibit the most potential to inhibit this virus compared to another extract. This potential extract inhibit dengue virus to 90.9%. Therefore, in this study, we interested to replicate the most potential good extract to utilize rapid identification of non-secondary metabolites in this crude extract. Okay, for the method, this plant was collected from Sematan, Sarawak, and this plant was going through the extraction process to give a total of 9 extracts. After that, screening of anti-dengue activity through the plot assay was done to determine the most potential crude extract that can inhibit dengue virus. The dichloromethan extract was then been analyzed using an LCMS to investigate data-dependent MSMS experiment. We use MZMine software for data processing and PID convolution. The application strategy began with the determination of molecular formula from the accurate mass measurement. Data mining using an MZMine 2.50 followed by the cross-search filter against dictionary of natural product produced a several hit. Okay, for the results, 31 peak were annotated. 20 peaks out of 31 peaks were matched from the NP database by using a taxonomy filter of Goniothalamus species based on the metabolite identification confidence. These 20 peaks were annotating at level 3 because it matched with the MS1 MZ database, while another 3 peaks were matched with the in-house spectral database by taxonomy filter of Goniothalamus lanceolatus at level 2 because it matched with the MS spectrum. Then sterolactone label, as the label is here, were confirmed. Sterolactone were confirmed from the isolated compound, and it was considered as a level 1 metabolite independent in identification confident because it matched with the reference standard confirmed structure. So these compounds, including goniolanceolate A, goniolanceolate E, gonodiol, AAP9-deoxygonopapyrin, gonifopyrin B, parvestin D, hydroxygonothalamine, and also deoxygonopapyrin B. Okay, for the conclusion, the replication revealed that sterolactones and astogenin is the major group of compound in this leaf dichloromethan extract. For greater confidence in annotation, combination of spectral MS comparison and molecular networking will be the way forward. Okay, that's all from me. Thank you and stay safe, everyone.
Assalamualaikum. My name is Siti Nuraina binti Syah Abdul Rahim from Faculty of Applied Science, University Technology Mara. Today, I would like to present a poster entitled Chemical Constituent of Tectona grandis leaf using Modern Advanced Chromatography Technique. The plant of the interest is Tectona grandis, known as teak or jati. Usually, these plants were active in furniture industry where the fact that the leaf of the Tectona grandis are disposed as waste material after the wood were collected. Phytochemical study done on the waste part may lead to the possibility to find useful application. So, the research are focused on isolation of chemical constituent from the leaf of Tectona grandis from methanol extract. For the methodology, The leaf was collected from Stesen Penyelidikan Free Mata Air Perlis Malaysia. The leaf were dried, grind, soaked in methanol to obtain the extract. Then we partitioned the extract using 3 different solvent polarity, which were hexane, chloroform, and aqueous. From the TLC profiling, aqueous fraction was selected for the isolation and purification process. The fraction was isolated by advanced chromatography technique using flash chromatography that optimized for rapid separation. The sample then were purified using preparative recycling HPLC to achieve complete separation of compound. The compound targeted was subjected into HPLC to obtain the profiling. Then the sample was tested with NMR to identify the compound. So from all of this process, we finally success to identify a chemical constituent of verbacoside, which belong to the phenyl propanoid glucoside. So the last but not least, the study was successfully isolating the compound from Tectona grandis. The finding was determined in order to scientifically rationalize its usage so that the compound may be further studied pharmacologically, which may turn waste material to wealth. That's all from me. Thank you.
Kita indah di mata dunia, hidup harmoni berbilang bangsa, wajah riang manis senyuman, sejahtera sealun senada sejiwa. Pantai pasir putih, lautan biru, dan siram ombak dihembus bayu. Hutan hijau malah berseri, bunga-bungaan harum mekar menawan hati. Malaysia indah, nadi hati jiwa kita semua. It's a truly Asia, Malaysia menawangi kehidupan bahagia. Malaysia, melawat Malaysia, pentas seni budaya dan bangsa. Visit truly Asia, Malaysia, segala bermula di sini, di Malaysia.
Selamat datang ke Malaysia.